Okay, class, in this lesson, you're going to learn to use a composition of rigid motions to show that two objects are congruent. Okay, so let's go ahead and get started. So first thing we want to do is identify what congruence means, right? So hopefully by now you understand that congruent figures means that the figures are pretty much the same size and in shape. Okay, so two figures are congruent if there is a rigid motion that maps one figure to the other. Now we've learned about three different types of rigid motion. That's translation, rotation, and reflection. Okay, and so in all of those rigid motions, you probably have seen that all of the objects that have moved, whether it's been translated or rotated or reflected, that they're essentially the same type of objects. Okay, now a rigid motion is sometimes called a congruence transformation because it maps a figure to a congruent figure. So a figure will go from one position to another. Now we also use the following symbol. So we got this equal sign with this squiggly line. And when we use that, we're using it to show that two figures are congruent. Okay, so in this example here, we say that since the reflection of triangle ABC, okay, reflection, this is the R for reflection, across the line M, okay, since that reflection is equal to triangle DEF, so we've got ABC is equal to DEF, then we would say that triangle ABC is congruent to triangle DEF. Okay, so that's just another way to say that both triangles are equal. Now notice the markings here on triangle ABC. Okay, so we've got a bunch of things going on here. So we've got this slash mark for segment AB, and we also have this one segment slash mark for segment DE. And basically what this means is this hash mark means that this segment is equal to segment DE. They're the same exact length. Okay, when we have two hash marks and two hash marks here, it means that segment BC and segment EF are exactly the same length. And then we've got three hash marks here. So segment AC is exactly the same length as segment DF because we have three hash marks here. Okay, so those are lengths of a segment. Now we also have another marking, which is this little arc here for angle A, and we also have one for angle D. And since these are both single arcs, we would say that angle A is equal to angle D. And then here for angle B, we've got two marks or two arcs here, and angle E has two, so then both of those angles are the same. And then angle C has three arcs, and angle F has three arcs as well. And so both of those angles are equal. Okay, so those are another way to specifically specify that the segments and the angles in this triangle is exactly equal to the segments and angles in triangle DEF. And since they're both the same, meaning they're equal to each other, and we have a reflection across the line M, then the triangles are congruent to each other. Okay, so let's take a look at this particular example, example 1, and we're going to verify congruence. Okay, so what we're told here is that given triangle XYZ, so XYZ, given this triangle is congruent to ABC, so we're told that they're congruent. The question here is, what composition of rigid motions maps this triangle XYZ to ABC? So in other words, what sort of translation, rotation, reflection, if any of those, has to occur so that XYZ maps to ABC? Okay, so the first thing we're going to do is rotate XYZ about point Z. Okay, so if you imagine, and I'll do this in a second, but imagine taking this triangle and just rotating this about point Z. Okay, so if I were actually to do that here, let me go ahead and group these together. So if I were to rotate this about point Z, okay, so now it lands over here. We've essentially rotated 180 degrees about point Z. So Z is our pivot point, and we're rotating this whole thing by 180 degrees. And then the next step says to translate the image 3 units to the right. Okay, so we're going to move this 1, 2, 3 units to the right. And when we do, you'll see that it lands exactly on triangle ABC. Okay, so this notation here on the end says that triangle XYZ is rotated 180 degrees about point Z, and then it's translated 3 units to the right. This is a positive 3, and we're not translating it vertically. Okay, so it's all horizontal and to the right. And when we do, it becomes equivalent to ABC. Okay, so we verified congruence there. Now let's go on to the next example. Okay, so now we're going to not verify, but identify congruent figures if they exist. So here's the question. Given triangles ABC, so this is ABC, triangle EFG, and triangle JKL, okay, which triangles are congruent? Okay, so on the surface, we see 3 triangles, and they all look pretty similar, okay? But the question is, which ones are exactly the same? Well, this one is a little bit more challenging, but here's what you can do. If we take a look at triangle ABC, okay, and we start to compare one side, okay, so let's say we compare side BC, okay, side BC to this triangle EFG or this triangle LKJ, okay, we see that to go from B to C in this segment, we have to go up 1 and then over 3, right? Up 1 over 3. Here, we can't go up 1 and go up 3 to get to G. Okay, so that doesn't work. F to E, that doesn't make any sense. We can go up 1 and then up 3, but it doesn't get to J. Here we can go up 1 and then over 3. So that matches KL. Okay, so BC matches KL. So we've got one side, and we've got a little bit of a clue that maybe this triangle and this triangle are congruent to each other. So that's verified. Let's take a look at this segment, the other leg, right? So we've got across 1, down 4, right? So we're moving across 1, down 4. Maybe if we move across 1 and then down 4, okay, that matches. So now we know KJ and AB are identical, and let's just verify the third side. Okay, to go from A to C, will we have the same effect as if we go from J to L? Well, to go from A to C, we're going to go 1, 2, 3, 4 over, and then up 1, 2, 3, 4, 5. Okay, well, going from J to L, we're going to go over 1, 2, 3, 4, and then we're going to go up 1, 2, 3, 4, 5. Okay, so now we've identified that ABC. So we're going to say triangle ABC is congruent to, and we need to specify the letters in order. So this will be triangle JKL. Okay. All right, so that is how you identify triangles that are congruent. We start with one segment and compare it to another and see if they match, and if they do, then you move on to the second side of the triangle, and then to confirm, you verify the third side. Okay, so let's go ahead and move on to example 3, and this will be the last example for this particular lesson. And now we're going to determine congruence. Okay, so in other words, we need to figure out which pairs of objects are congruent. And if they are congruent, we need to describe the composition of rigid motions that maps one to the other. Okay, so let's take a look at this particular figure. Okay, both these puzzles look like they're similar. And we see, hopefully we can see that if we reflect it across this vertical line, right? So if you picture this piece being flipped over to this side, so this becomes a mirror image, we see that the rigid motion is a reflection. Okay, so the pieces are congruent, the pairs of objects are congruent, and the rigid motion is a reflection. Let's move on to B. All right, so first we're going to take a look at both of these objects, and we see that they're not exactly the same, because if you take a look at this diagonal here, or this corner, we see that the length of this corner is significantly longer than the length of this corner. Okay, so we can't even say that that's a rigid motion because these objects are not even congruent. So we would say not congruent. All right, lastly, we've got these final pairs of objects, okay? And we want to know if they are congruent, and it looks like they are, because look at this red rectangle and this rectangle. They seem to be about the same. We've got this blue rectangle and this blue rectangle. They're about the same. We see this smaller red rectangle and this smaller red rectangle. And we've got this gold rectangle here. They kind of match. And then we've got this green and this green. So it looks like they are congruent, okay? So now that we've determined they're congruent, we need to identify the rigid motion transformation, okay? Now this one is a little bit more difficult, but bear with me. Picture this particular object, okay, rotating 90 degrees clockwise, okay? So rotate 90 degrees clockwise, okay? So when we do, and if we were to put it on top of this piece, we'd see that this red is actually from here to here, okay? And this blue piece would actually be down here, okay? So it doesn't quite map to this, but if we were to flip it over, okay, so we reflect it across this line here. So let's say this is our line of reflection. Okay, that becomes our reflection. So now we've essentially moved this side over to this side and this side over to this side. We see that it maps perfectly. Okay, so then we would say that this piece is congruent, and what we did was a rotation of 90 degrees and a reflection. Okay, so that would be our rigid motion transformation for part C. Okay, hopefully that made sense. If any of this was unclear, please go back to the beginning of the video and listen to this again. Thank you.